So what we want to talk about is how to implement searching and how to implement searching efficiently today. That's kind of our goal. If you remember right, but going back a week or two, part one, we talked about, what is this thing, MongoDB, what are NoSQL databases and why do we really want them? What are the benefits of using a NoSQL database over using a traditional relational database? So we talked about that. We talked about how to get Mongo set up and how to put your data in there. In part two, we talked primarily about how to implement CRUD in terms of being able to manipulate that data. With a little bit about, we talked about the find method in terms of being able to read data, but we really didn't spend a lot of time on the reading data side. Okay. So that kind of orients us with where we are. What we're going to go through today is to talk about how to implement searching and how to implement it in an efficient manner where, the database is doing most of the work rather than you're doing a lot of the work in the client, which just takes up a lot of memory and is a lot slower than having the database do the work. So that's our goal today. That's really important because 90% of your users' time will be spent really reading data more than manipulating the data. They'll spend most of their time browsing and looking for things, whether it's scrolling through a social media feed, whether it's looking at their recent transactions, whether it's looking at things in a shop or whatever it may be. Most of the users' time is spent really searching data or viewing data. And that's actually where I'd say MongoDB really shines over MySQL. There's a lot of things that you can do much more efficiently in Mongo if you understand the tools than I think what you can do in MySQL or other relational databases. Okay, so let's talk about searching. So we're going to talk about a few things today. First of all, we'll talk about indexes, and those indexes play a very key role in everything we're going to do today. So that's where we're going to hit them first. And you really need them to hit point two, which is to implement text search. You cannot implement text search without first creating an index. So we're going to talk about indexes and some of the indexes that are available. And then we'll talk about text search. We'll talk about aggregation pipelines, which is basically the MongoDB equivalent of select statements. So aggregation pipelines allow you to do a lot of stuff with your data, whether it be from things like, for instance, if you want to do a join, you do it through an aggregation pipeline. And a lot of other pieces, a lot of more complicated queries that you may want to run, with group by and order by and all these things, you can put those into an aggregation pipeline. One of the nice things about aggregation pipelines is that they're built up as arrays of JSON objects. So they're actually really, really easy to create, a lot easier to create than, say, creating a SQL select statement, because as it turns out, objects are easier to create with code than creating a string that's in a completely foreign language. So while SQL uses basically a completely different custom language to do its queries, I think as we get into it and you get used to it, you'll find that language is almost more natural and easier to work with in real world applications than SQL is. Next, we'll talk about a little bit about analyzing queries and some of the tools that are available. We won't go too deeply into that, but I want to give you some tools there, and that partly because that ties together the things we're talking about. So like, for instance, when you analyze how queries run, you'll see that it actually runs everything, even including a find, always runs as an aggregation pipeline effectively. whatever queries you run against the database effectively run as aggregation pipelines. So they're a fundamental tool there. And when we analyze queries, you're also going to be able to see some tools that tell you what index is it using, and potentially why did it pick that, maybe some hints on why it picked that index, or ideas of where you might be missing an index. So looking at how to analyze queries is important in terms of kind of tying things together. And then finally, we'll talk about how to stream results to the client. Basically, the idea being that normally what you do, and what we've done so far, is we say, let's get all the results that we want from the database and load those all in memory, and then send them all to the client. The problem with that sort of procedure is that the client really has to wait a long time, especially if your queries are more complicated, or if you have a lot of data you need to send back. So the client might be sitting there and nothing happening for seconds, if not minutes. Without that, streaming allows us to send the results piece by piece and show them as they come in, so the user can kind of see results earlier on, rather than having to wait for all the results to come in, and that in the end leads to a better user experience. So cool. So let's dive into indexes. So review a bit. Indexes support the efficient execution of queries in MongoDB. In reality, indexes support efficient execution of queries in any database, regardless of what database system you're using. Indexes are important for executing those queries efficiently. So without indexes, MongoDB has to perform what's called a collection scan, or scan every document in a collection to select the documents that match the query statement. It's a big deal if you have, say, 1 million documents in your collection, and it has to look at every single one of those. It will take a long time, right? So indexes are all about reducing the number of records that Mongo has to look at. Cool. So it's going to use that index instead of directly looking at all of the documents. So that's where it becomes valuable, because that's scanning the documents, and the number of documents it has to look at tends to be the thing that's most correlated with the time that your query takes. So the fewer documents it has to look at, generally the faster it will be. So indexes are a special data structure that's used to store a small portion of a collection's data set in an easy traverse format. And by easy traverse, I mean in a different format than how it's actually stored in the collection. You can think of the collection as just a very long list or array. It's in reality a little bit more than that, more complicated than that, because, for instance, you usually have more than one server running MongoDB, so you might have a cluster of 3, which means that part of that collection is actually probably not, that whole collection is probably not stored on one computer. So it may be 1/3 of that collection is stored on computer A, a third of that data is stored on computer B, and another third of that is stored on C. So it may actually go to all 3 of those servers to pull out the entire collection. And we do that because of performance. It actually can be more efficient to split that data up over multiple servers, depending on the situation at hand. So that's one of those things to keep in mind as well. So generally that format is some sort of what we would call tree structure, that index. So it's structured in a way where you can do things like a binary search. You may have remember hearing this term binary search or linear search in your C# course. And you'll remember that a binary search takes significantly less time. Formally, we would say, scanning through all the documents, scanning through everything takes linear time. It takes rough, an order of magnitude equal to the number of things you have, versus doing a binary search takes logarithmic time. because if you have, let's say, 256 records, that's 2 to the 8th, it may only take 8 seconds, whereas it would take 256 seconds to scan the whole thing. So it's a really big improvement because it's a whole different order. It's not just an order of magnitude; it's a different algorithmic or cyclomatic complexity, as we'd call it formally. So that's important that those things are stored as basically a tree structure, and that's actually true with indexes in most databases. Typically, an index is some sort of tree. That's not the only way to create indexes, but that's how most indexes are. So the index stores the value of a specific field or set of fields, and that's going to then be ordered by the value of the field. So whatever's in that index is just the values that you've told it to index. So for instance, if I told it to just index the name of the product, then the only thing that's in that index is the name. Everything else you have to go to the table to get. Similarly, if I index the price is the only thing in that index. If it wants more columns than that, then it needs to again go to the collection. But even that, because we're looking at fewer documents that way, is still a plus. So the ordering of the index is still used. So that ordering is used both for the equality or range-based matches. So because it's order, if you have an index on price, then it can support things like, I want all the products that are between $10 and $100. Well, it can go find that because they're already ordered by the price. Similarly, if you want to sort the results by the price, that index on the price also supports that. So it's not just used, it's basically, you can think of it as being used for your where clause, but it's also used by your order by clause. Okay. So it's needed for both of those parts to make them efficient. Now, in some cases, you may have more than one index. So maybe I have an that applies. I might have an index on the name, and I might have an index on the price. Well, if the user's looking for both by the name and by a price range, then it's going to have to pick one of those two indexes, or it may use a combination of those two indexes to fill the query. So to kind of give an example of how this works out, here's kind of a diagram of that. We're going to say users, take the database, users.find. So we're going to find the users with a score that is less than 30. And then we're going to sort it by the score in descending order. So remember, find, you give it these sort of filters with different operators. So and so we're saying less than 30. I think these quotes in here are actually optional. And then when you say how you're going to sort it, 1 would be ascending order, -1 would be descending order. So that's where I'm saying this is descending order. So if I look at my index is kind of the structure in between, and it looks like a line here. In reality, it looks more like a tree. But then I have beneath it, here's the collection. This is the actual data. And so if I didn't have an index, I would have to go through every single document down here in this collection to go find those users. But because I'm using this index on the score, I don't have to go down there. So instead, I'm going to look into the index and say, well, I want everything that's less than 30. Yep.
Yeah, your audio is cutting in and out. I think we have to optimize your microphone sensitivity. I don't think it's a bandwidth issue.
I will have to check.
It was okay before, but it's kind of getting worse now.
Yeah.
Yeah, I get it too.
Okay. Can you hear me now?
Yeah, it seems to be better. We'll see.
Okay. I adjusted a little bit, so we'll see if that makes any difference. Let me pull it down a little bit there. Okay.
And so far, so good.
Okay. So it was trying to automatically figure out what the breakpoint was. I but I thought I had it set to manual. So anyway, I switched it back to manual and set it at, I think, negative 85 dB. So we'll see if that works. So that's kind of our index, is that structure in between that optimizes things. So in here, because the index is effectively sorted by the score, I go to the point in the index where 30 is, and then I just traverse all the way to the left. So we say, okay, this is the one that's 30. This is where the 30 mark is, and then I'll go visit all of the documents that are less than that. So as it turns out, in this particular example, that means I only have to look at those 3 documents. And because I'm traversing it from left to right, they will be read out in that sorted order. So I'm going to go visit score 25, and then follow this arrow, score 18, and then score 5. So they'll come out in that order of descending score, just by the way I traverse them. Okay? Questions on indexes? Anything you missed because my voice cut out?
The query that you're doing there, that's probably best just to do that straight up in Mongo shell, right?
Well, this is the syntax for shell. It's a slightly different index. It's a slightly different syntax if you're going to do it through Node. Namely, that here you would have collection and the name of the table. But other than that, it's pretty similar.
Okay, so it's shell. That's one verify.
Yeah, this example is shell, and by the way, most of these examples will be using the shell syntax. Later on, we'll get back to the Node sort of syntax, but most of these will be in the shell syntax. The only thing to know there is they're very, very similar. The only thing that changes really is how you select the collection. Other than that, the shell and the node are pretty similar. So you'll remember we talked about how to create indexes in Compass. So you can do that using the UI. It is worth noting that not all indexes can be created through Compass, and specifically the one that we're most interested in today, which is used for text searching, in addition to ones that are used for geographic sort of searching. Those types of indexes are not actually creatable in Compass. Okay, so you can create some indexes, but there's a lot of indexes that you can't create. And in general, I'd say it's faster to create indexes actually on the shell. So I want to talk about briefly how that syntax looks. If I want to say create an index on the shell, I just say db.collection.createIndex. And here I would put the name of the collection, and then I put there's two parameters to the create index. First is the actual information about what columns are you going to index, and then the next part is some additional options that you might set as far as the particular indexes that you're creating. So for instance, if you want to make a unique index, that would be something you're going to set in the options. Okay. So what you put in here, and kind of look at an example, let's say I want to create an index on the name. I would start by db.products.createIndex, and then we're going to say name1. So name1 says that I want an ascending index on the name. If I said name -1, that would be a descending. In general, I'd say create most of your indexes in an ascending order is usually the better of the two. There's very few cases where a descending index makes more sense. Okay? Questions on that for the shell syntax? This is basically what it looks like.
What other options are there?
We'll talk about those. That's a few other slides. Okay, so this is your basic syntax. So if I wanted to say, for instance, index 2 columns, I would say name and price, I would say name 1, price 1, comma, price 1. And that would index both of those together. That creates something called a composite index, which is useful in some scenarios, but usually not what you want. So usually if you need an index on multiple columns, you want to actually create those as separate indexes. So this is create an index on name and then create a completely separate index on price. That's what I would stress. But this is all you need to know as far as creating them on the shell. That's usually the easiest way to create them. One of the benefits of actually doing it this way too, let's say you want to store a record of all the indexes that you created so you remember what they were. Well, I can easily take this code and just toss it in a text file, and then I can know what indexes I have on my database. Does that make sense? Versus it's not as easy to, say, document it if I'm doing it in Compass. But this is fairly easy to document. You just write that into a script, and then you can reproduce it. So let's talk about some of the, before we get to the options, we need to talk a little bit about the types of indexes that are available. Because there's actually more than one kind of index available. So MongoDB provides a number of different types, and these types are used to support specific kinds of data and queries. Okay, so the basic one, which we've kind of seen already, is your just simple single field indexes. So those are where you just say, I want to index this single field, which is like the score, the price, the name. And these ones are actually, as it turns out, are the most common and oftentimes the most important ones, because they support your basic queries such as equality and range-based comparisons. And so for these single field indexes, the index key typically does not matter, because Mongo can do it either front to back or forwards to front. So if it's ascending versus descending, tends to not matter. So that's where I say usually you make it in ascending order, which is just setting that to 1. You can also create compound indexes. Compound indexes are over multiple columns. So for instance, here we're creating an index over the user ID and the score. Now you'll notice here this particular index is ascending order on the ID and then descending order on the score. So in this case, the order actually does matter quite a bit if you're using a compound index, because it can only use it to sort it if you're specifically using that order. So if I sort it by user ID ascending and then score ID descending, it can use this index. But if I change any of those, let's say I sort by both of them ascending, this index isn't going to apply. So the order of this makes a lot more is a lot more important if you have a compound index, because it can't always use it for the sorting purposes.
Now, I'm trying to think why. If you had two single indexes, one user ID, one score, what value does this add? What does this get? And I don't see what bearing sorting has on it at all. Like, what does that have to do with anything?
Right. So what this does in a compound index, this specifically makes queries faster when you're using both of those. If I'm saying, for instance, give me the users that have a user ID greater than 50 and a score less than 20, that would be potentially where this index would come up, right? So if I have both the user ID and the score effectively in my where, then this index would be used. Does that make sense?
Okay, sure, but what does the ascending or descending order have to do with it? How quickly would it work?
It has to do with sorting the results. So if I say sort the results in this order, then it doesn't have to sort them. Does that make sense? Otherwise, it has to do additional sorting pass to get them in that order if it's a different order.
Oh, all right. So in this case here, it'll give me the user ID starting at, okay. You
So
don't really manipulate that when you get your results back, right?
you're going to manipulate it on, you want the database to do the sorting. You can do it in Node, but it's better to have the database do your sorting for you. And that's true with relational databases. That's true with any database. It's always better to have the database do the sort.
Okay, so that's why you were saying if we have another compound index on user ID and score with a different sorting order, that ain't going to work. It's got to be just one.
What do you mean?
I thought I remember hearing something like that. Well, right here we have user ID ascending and score descending, right?
Right.
Could you also create another index where it's user ID and descending and score ascending?
Yes, I believe so. You could create another index, same columns, but different sorting order.
All right. It's probably too much minutia. So
it is. It is.
Yeah, okay.
I would say that for the most part, and we'll get into the tips, I would say most of your database probably should not have compound indexes. Compound indexes are a very easy thing to get into trouble for because they're honestly most of the times very rarely used. They're only used with very, specifically with queries that reference both of those columns. So a lot of times that's hard to guarantee. Most of the time you can't guarantee that two columns will be used together. Plus, if you're doing a text search, these don't get used at all, basically. As it turns out, you're probably not going to create very many compound indexes because they're usually a bad idea. At most, you might have one compound index on a collection. Usually, that's kind of your top. The one place where these do become really useful is when you need them to be unique. Okay. So what I could do is mark this index as unique, and then the combination of those two columns would have to be unique, that pair. So for instance, if I'm saying I want my votes to be unique, then I would say the user ID plus the thing they're voting on. So say user ID plus product ID, those two things, that group needs to be unique so that they can't cast more than one vote or more than one rating. Does that make sense? So compound indexes are more used, I would say, for enforcing unique constraints and less used for performance. Because they're a lot harder to say, there's a lot fewer cases where a compound index actually speeds things up compared to a single field index. You also have another kind of index, which is a little bit nuanced, called a multi-key index in Mongo. A lot of times these multi-key indexes look very close or almost identical to your regular indexes. The trick is they work anytime you have, they're used to index fields within an array. So what that means is, for instance, let's say we have this user collection, and inside of the user collection, they have an array of addresses. So each of these users has more than one address, which means they have potentially more than one key for different things. So maybe I want to index the zip code inside of the address. Well, the user, because they have more than one address, they have more than one zip code. Got it? So, for instance, in here, the index needs to point, say, 100.100.36.94.301. Both of those point to this user XYZ. So there's actually two entries in the index for the same document because of this sort of structure. So we define these the same way that we would with a regular index. Here I'm going to define this as address.zip. And I do need to put quotes in there because there's a dot. But that will then index all of the zip codes within the address. Paul, you were trying to say something?
Yeah, with with all these indexes and understanding going to NoSQL database, the amount of storage that everything takes up is cheap. Why not just go whole hog and do it on everything? I mean, why not? It's not that big, right?
Oh no, it's a cost. It's a cost. Part of that, it's really the amount of space that the index takes up is not a big deal. Indexes always take up less space than the collection itself. So in terms of storage space, they're very cheap. What they cost is there's a maintenance cost on them. So anytime you change the data, that also triggers an update to every single index on the collection. So if I have 100 indexes on my collection, it's going to be a lot slower to update that data.
So you have to optimize the indexes because they do help the searches, but if you got too many, it's going to cripple it. So it's,
So the trick is to add the ones that are actually going to be useful and helpful, that are actually going to deliver a noticeable boost to your searching, to your user, without adding so many that it becomes a burden. So the correct number of indexes, I'd say, usually is somewhere between somewhere around 5 per collection. I'll break that down in a minute about what those should be, but usually I'd say it's 5 to 10 indexes per collection basis. 5 is usually not necessarily a huge drain on performance for a lot of times. Really depends on what you're bringing in. If it's time series data, that may still be a lot, but 5 index is usually manageable enough, and delivers good performance if you pick the right set of indexes. Okay. So that's what a multi-key index is. A multi-key index is on a field that's inside of an array. So one of the things you'll notice there, I'm kind of skipping the fact that there's an array when I define this. So I've got, the square brackets and then the curly braces, which represents an array, and then an object. I don't actually specify those as part of the index. You see that?
Yeah.
So it's a little bit weird when you're defining the index that way, but these are actually really useful because I can do things on that. For instance, let's say I've got, articles or tweets have an array, or blog posts or whatever it may be have an array of tags or an array of categories or whatever you want to call it. This kind of multi-key index applies for that because it can then put that in for every tag it has. So it's not just the point is it's not a one-to-one. It's not a one element in the index equals one element in the document itself. It means that there's actually more entries in the index than there is in the document. And where I said, most of the times, for the most part, I would say indexes are much cheaper, use much less space than a collection. Multi-key indexes are actually a weird one where if you have a mismatch, this can actually be the index can actually be bigger than the actual collection. Because if I think of, let's say I have 100 documents, but each of those 100 documents have 1,000 tags, well, I might only have 100 documents, but I have 100,000 entries in my index. Does that follow?
Yeah.
So these are tremendously useful. Don't let me discourage you from using these. Like, multi-key indexes are one of the most useful things from having this document structure. They are tremendously powerful, and they tend to provide a lot of value if you have queries that need them, that are going to use them. But they can't actually take up a good amount of space if you have documents that have a lot of subdocuments. So one of the ways around that is to kind of limit how many subdocuments and how many things it can have inside of it. So you might say, well, it's not sensical for my products to have 1,000 tags. We'll just say, well, they're limited to 10 tags, and problem solved. So the next kind of index that you can create, which is special, is what's called a text index. So text index is used to support searching for string content in a collection, and these text indexes, they're kind of stored in a different way. So whereas the other kind of indexes that we talked about previously, they actually store the value of the key and let you to do equality and range checks. This is actually used for like a keyword sort of search, like you might have with your search bar. So it'll, rather than keeping the individual values and being able to do equality, it's able to do things like, okay, save all of the words that are in the document, and then if you're going to go look up that word, it'll say, okay, well, here's the documents that have that word in it. So if I want to look for red, well, they'll give me all the products that have red in them. If I want to go look up for boots, well, they'll give me all the products that have boots in them. And it actually stems it down to the root words. So things like boot and boots, it actually resolves most of those plural versus singular differences. So story and stories, it can even figure those things out. Because it'll turn both the search term that you put in and the word that's in the document, it'll put that down to the root word story, so that you can do stories or story in both places and it will still find it. So these text indexes are even better than just does this text contain the word that I say? With me?
Yeah, and it searches every field in the document to see if anything matches it?
It searches all the fields that you tell it to index. Okay, so when you set up the text index, there's a few ways you can set it up. So I might set the index up to say, let's only search the name and the description. And at which point, if you do a text search, it's only going to search the name and description. But there's another way to set up, but when you're setting up text indexes, I typically will set them up with what's called a wildcard. And if I set them up with a wildcard, then it does actually index all of the fields. So you can set it up to index just some of the fields, or you can tell it to index all of the fields.
Got it.
Which is amazingly powerful. And that's one of those things that a relational database cannot do. Like MySQL cannot do that, because it can only index, your full text index can only index the things that are in that table, right? So you can't index something that's in another table. So for instance, if I say with a relational database, typically I might have the author of an article. Well, if the author name is usually in another table, it's not usually directly in the article, I can't actually search by article. I can't actually search by author because that string is not in the blogs or the posts table. Does that make sense?
Yeah.
So if I denormalize things, I put a copy of that name into the blog document, the post document, then I can actually search by author name, because then it will be in that text index. So we'll come back to text indexes in a minute, and I'll talk about how to create those and how you can set those up. Another kind of index that exists and is actually really useful is geospatial indexes. And these are used to support efficient queries of geospatial coordinate data. So MongoDB provides two kind of indexes for this. The first one is a 2D index, and the second one's called 2D sphere. 2D index just treats your places as on a two-dimensional plane, which is good for things where you're really close to it. So you might think, maybe if I'm looking for stores in St. Louis, that's pretty quick and it's pretty efficient because I can treat St. Louis as flat. But if I want to search globally or even nationally, then the curvature of the Earth starts to matter. So that's where you would use a 2D sphere instead, is if the curvature of the Earth is significant enough to matter, or you don't know. Sometimes you may not know how far it would be away.
That's latitude and longitude, right?
Yeah, latitude and longitude.
And versus Google Earth, something like that.
Well, they're actually both the 2D and the 2D sphere use latitude and longitude. It's just that the 2D models the Earth as flat, and the 2D sphere models Earth as spherical. The difference is that modeling things in 2D takes less number crunching, so it can be quicker. But the problem is that the 2D does not work so well if you're further away. Right? It breaks down the higher the distance is. Got it?
Yeah, I think I got it. I see it's outside the scope.
We're not really. I think most of the projects we're doing and are going to do aren't really going to use this. There are definitely projects that you can take on where this is tremendously useful, which is where I want to mention it. So, if you are doing something where location is an important part of what you're doing, such as I think you were doing something with TripAdvisor type system, Paul, that's where you may need one of these, to be honest. You might want to be able to say how far away is that location. But if you're just doing something that doesn't involve location data, which is, I think, a lot of people's case, then they're not that important, which is why I'm not going to say too much about them. But if you do want to read up on them, the links to them are there. Another kind of index that exists is something called a hash index. And hash indexes are kind of weird. They're good for things that where you kind of want to do an equality match. They're only useful for equality matches. They're not usable for range matches, as we said. So you can't do less than or greater than. It can't support those kind of queries. It can only support queries where it's equal to. Typically, the only place these are used is for things like if I have a really long description that I want to somehow match, or if I have like a hashed password and I want to match hashes, things like that. Then these can be useful. If the thing that you're trying to do equality with is fairly long, the hash, as it turns out, is shorter, so it can be helpful. Okay. So for instance, or another case where this might happen, let's say you're looking, for some reason you decided to store other sorts of binary data, such as images, in your database. This would be the only way to do any sort of match on that data. So these don't usually come up very often. I don't think you'll have a case where you need to use them, but they do exist. So just a few tips about how to pick your indexes and what indexes you should have. So you should create single field indexes for all fields that either any of these, at least one of these things is true. Either it must be unique, if that, let's say the name of the product must be unique, or the name of the place, or the username. If that column must be unique, then you should definitely create an index on it and mark that as a unique index. If that index is something that the user could filter on, say filter by category or filter by price, or all sorts of other things, filter by size, filter by color, if they're going to potentially be able to filter by it, you should index it. And you should index everything that they can filter by. And so you should have a single field index for that. So that means, let's say I'm talking about cowboy boots or the cowboy boot store. I should have an index on the name. I should have an index on the category. I should have an index on the size. I should have an index on the color. I may have an index on other things as well, such as maybe tags, if there's tags. So you should have several single field indexes. You should not just have one, typically. You're going to have one for everyone there. You also want to use those anytime that field is going to be used with a lookup. And lookup we'll talk about in a minute is with our aggregation pipelines is to do things like joins. So if you're going to join on that value, you should index that value. Okay? So, and roughly speaking, every collection you have should have 1 to 5 single field indexes. Typically, that's kind of the happy range. If you have no single field indexes, that means that any query that you run pretty much is going to have to go back and look at every document. Does that follow?
Yeah.
You know, if you don't have any single field indexes, you're very likely to run into a collection scan. So you should always have one, because there's always going to be something that's like, well, what is the most common thing for me to look at? And usually that's the name. So usually the name is a good place to start as your, well, that should have an index. You think about what is the most important piece of data in there, index that, and then think about additional things that the user might want to filter the data by. So I would create single field for each of those. That way the user can slice and dice the data based on any of those just single field indexes. And then the database can decide, which one of those indexes is going to be the most efficient. I would say, if you're going, you can definitely go above 5. And it really depends on what you're doing. But I would say 5 is a pretty good end cap, namely because they really correlate to, let's say you've got drop downs or input fields on the search interface. If you have more than, you're probably not going to need to have more than 5 filters on your search interface for this class, right? I would expect you to have maybe, 3 things to filter by. But I wouldn't expect you to have like 10 different filters. Does that make sense? So kind of, that's kind of where I would play that. Single field indexes, there should be 1 to 5 per collection. A text index, then, you only create 1 text index. Collections can only have 1 text index on them. You can have a text index for each of your collections, but they can only ever have 1. Okay, so your products cannot have 2 text indexes. It's only 1. In there, you decide what index, what columns, or sorry, what fields are going to be in that index, but you can only have 1. Not all of your collections necessarily need to have text indexes. They're just going to be the ones that the user is going to search with any sort of keyword search. Okay, so if we're thinking about, for instance, the emoji database, right? Remember, we had emoji, we had users, we had votes, and we had reviews. Well, what of those 4 tables should have a text index? Reviews would be a great thing, because yes, we're probably going to search the reviews by some text. What else? Is the user going to look up emojis by keywords?
Yeah.
Probably, because it's like the main thing on our table in our database. Like you can think of if you're having an e-commerce store, well, products is your most important thing. So the user's obviously going to need a text index on products. So emojis is kind of the same thing. So emojis should have should have a text index. Reviews should. What about votes? Should votes have a text index?
No.
Why not?
Well, you don't have any text in there.
You're right? You wouldn't do a keyword search on the votes. You do like an equality search because you want to know what emoji, what thing did they vote on or who did the vote. But there's no need for a text index on the votes. What about users? Should users have a text index?
No.
Why not?
Trying to think.
Would anybody be interested in doing a keyword search on your users?
Hopefully not.
I don't think they would.
What if you
username?
Yeah, well, what if you have a user that you really like and you want to go see his opinions on et cetera things? Like, let's see Steam. Maybe you have a reviewer that you really follow his reviews. Would you want to look up that users and see their reviews?
Yeah.
Probably, yes. I would say that users in general are a good thing to still have a text index on. How much you use that text index really does vary. So, I mean, if I'm saying, Facebook, for instance, a text index there is pretty important because I'm searching for profiles potentially. Same way with LinkedIn. That's a place where having a text index on my users is really important. If I'm doing it as something where maybe your normal users can't search for other users, it may not seem as important, but what's going to come down is that your admin more than likely at some point needs to be able to search for users. So even if your regular users aren't doing a search, it's likely that you need an admin interface to manage users and to manage users that maybe are doing malicious things or just have names that violate your terms of service. You need the admin to have some way to search for users based on, say, their first name, last name, username, email address, things like that. So you really should have a text index on your users table as well. With me?
Yep.
So in that scope, the only one that doesn't get one is votes. And that's basically because there's no textual data. And you'll find that sometimes. Especially things like, an order. An order may not have a lot of textual information in there. I still probably would have been able to search it because I want to say, when have I ordered this product before? And what did I get? So there's still some value to having an index on orders, but sometimes things like that, maybe you're not going to do a search on. Any collection that has any sort of geospatial information should get a geospatial index. So if you have latitude and longitude information, you should index that latitude and longitude information, period. Because that's necessary to do any of the math and the searching with any searching based on location. So let's say I want to be able to find all of the restaurants that are near me or your retail locations that are near me. That's where I need a geospatial index there. If you have latitude and longitude information on your users for whatever reason, that would be something I would index as well. So I can know, search for users based on their location on the globe. So anytime you have that, pretty much you're going to want to index it, because if you have reason enough to store the latitude and longitude information, as long as you have reason to store geographic information, you have a reason to sort it. You have a reason to search it. If you didn't have a reason to save it, then you wouldn't have a reason to search it. They really go together. So if you have that data, you should be able to search it. Okay? Multikey indexes would be for, things that you have arrays that's going to be filtered on. So let's say you have an array of tags, array of keywords, genres, categories, addresses. Any of those sort of things are things that you would put a multi-key index for. And then finally, only add a compound index if it would have a The rest of these indexes, especially like single field indexes, text indexes, you can see I say, well, you should add them even if not all your users are going to use them, because at least enough users are going to get benefit out of them to make it worthwhile. The thing about compound indexes, the Mongo can always use one of the other indexes in place of a compound. It can always use one of the other indexes as a replacement for compound. But oftentimes compound cannot substitute for one of the other indexes. So they're a very narrow use case where they're actually helpful. So the only time you should add them is if you're seeing slow performance without a compound. Does that make sense? You should only add them if things are slow and you can tell that adding it makes it faster. If neither of those things are true, it's not slow, or adding it does not make it significantly faster, you shouldn't add a compound. So one of the things that means is you really should build and get the application working before you even think about adding a compound index. The one exception to that rule is if you have a group of columns that need to be unique, then go ahead and add a compound index to make those unique. But other than that, those are usually things that you don't add until you have a working application and you can actually measure performance. Okay. The other kind of indexes, single field, text, geospatial, multi-key, you can typically anticipate what the usage is going to be and what indexes you need. Before the application is up there and running, you can usually make a pretty good educated guess. Compound indexes are a different story entirely. Okay. If you're going to say create a compound index for uniqueness, then, for example, talking about specific things like things in your shopping cart or order, you might say, well, the combination of user plus product need to be unique. If you're talking about ratings, the product plus the user needs to be unique. Review, user plus that needs to be unique. But all of these are cases where you need a combination of two columns. In all of these cases, it's the user is at least one of those columns, the user and what thing it applies to. That combination needs to be unique. I would create that with, for instance, let's say we want to say things in the cart need to be unique. You'd say db.carts.createIndex, same syntax as we've seen earlier. I'd say user ID 1, product ID 1, and then unique is true. So this is where I'm adding that options. So in this options, I'm saying that unique is true. Cool. Similarly, if I want to force ratings to be unique, I would say user ID and product, well, that needs to be unique. Any questions? Unique indexes?
No.
Okay. Any questions on here? Kind of general tips of what indexes to create? What are the most common kinds of indexes does this mean that you're going to be creating? Singles. And then what would be second most common?
Text.
Probably text. And third to that would be things like multi-key. But single field and text are going to be your most common two kinds of indexes that you'll want to create. Okay, so let's talk a bit about text indexes. So MongoDB provides text indexes to support text search queries based on string content. So it's important to note that this is for string content. Your text index cannot index anything that is not a string. So for instance, numbers and dates cannot be put into a text index. Got it? It's only strings, only text. So text indexes can include any field whose value is either a string or an array of strings. So if I would say I can index the description, or I can index the tags because it's an array of strings. So those are the things that can index. So if you say, for instance, you index the price, but you try to tell it to index the price, it's going to go ahead and give you that, do it and not give you an error, but it won't put any of those prices in there because they're all numbers. It's also important to note, as I mentioned previously, that a collection can only ever have at most one text index. Your collection cannot have two text indexes. It's only one. So whereas all the other kinds of collections, you can create as many indexes as you want, text indexes, it's a one for one. Your collection either has a text index or it doesn't. So creating text indexes, you're going to need to do that through the shell. They cannot be created through Compass. So if I want to say, so the basic syntax for indexing something would be, for creating a text index, is as follows. So let's say I want to index just the name of the products. I'd say db.products.createIndex, and here I'm going to say name text. Remember previously I'd said like name 1, negative 1. Here I'm saying name, I'd said the name of the column, and then 1 or negative 1. Here I'm saying text to say it's a text index instead of a single field index. Got it?
Yeah.
So that's what changes it to be a text index, is putting the word text there. You can also create composite text indexes over multiple fields. So here I would create an index on the name, description, and the tags. So all of these would be included in the text index. So if I do a text search, it's always going to be over all three of those columns, the combination of the name, the description, and the tags. It's worth noting, once I've created this index, because there can only be one index, I can't then just search on the description. I have to search on all of those columns that are indexed. Okay, that's generally not a problem. That's pretty much, if you're going to index it, you're going to search all the things that have been indexed. So that's typically not a problem to say that, okay, I'm going to include all those things. Okay. The third way that you can then define these text indexes is using a wildcard, which I mentioned previously. The special syntax for a wildcard is $***. So here I'm creating an index on every field that has text content.
So in general, we're doing this for when that last option. That's probably what we would do.
Yes.
With that.
Yes. Most of the time, this is the best thing to do, is to just say, I want to index everything that has text in it. That's usually the best option to ensure that everything gets indexed. The downside to that is it's a little bit more expensive for it to do the indexing, to keep the index up to date. So this is a little bit faster than that. Anytime you go to update or update, insert, or delete records, documents. However, the cost of doing this is usually small enough that it's worth doing it for the benefit. Does that make sense?
Yeah, and for what we're doing here, it's not like we got millions and millions of records. We got maybe 100 at the most.
Well, it's actually doesn't matter how many records you have. It's not a question of how many records you have. It's a question of how many users you have using the website at once, and how willing they are to allow for a little bit of wait time. Does that make sense?
Okay. Yeah.
So doing it this way instead of doing it that way adds a little bit of delay when they hit the save button, but it's usually so small that it's not noticeable. Does that follow?
Yeah, that makes sense.
So it's usually in your trade-off that this is worth the additional cost. Anytime you're creating an index, I would strongly recommend you give it a name. This applies to any kind of index, but it especially applies if you're creating a text index. I would definitely make sure you don't take the automatic name for text indexes, and especially the wildcard index, because it's kind of weird what it names it. So what I would recommend instead is call it, with the options, specify the name of the index. So here I'm specifying this is a wildcard text index, so it's going to index everything, and then we're going to name this text index. I would do that same thing with all of these. If I was just going to index the name, the description, and the tags, I would give any of those the name text index, because remember, you can only have one. So if I'm creating just a single field index on name, I would, or price, I would name it price or name. So generally, I would say, if you're going to create an index, give it a name. It kind of forces you, if you're using Compass, that it's the first field you enter. It forces you to enter a name. The shell does not force you to give the index a name, but you should. Okay, because the name you give it will be better than the one it picks automatically. Because the names it picks automatically are not really all that intuitive.
When will we reference the index after it's created? It seems like you just fire and forget, move on. If I created it, great, that works.
The most common place you're going to reference it is if you're going to delete the index and recreate it. So if I was, say, creating an index this way, over name, description, and tags, it might come along later that I need to add an additional column that I'm going to index, which might be something like the author name or whatever it may be. Then I would need to delete the index and recreate it. And in order to delete an index, you have to know the name. Does that follow?
Yeah, I see.
There's also, when you're creating your aggregation pipelines, you can give it hints about what index to use. And in order to give it that hint, you have to tell it the name of the index. So it's both for being able to delete and recreate that index, as well as for being able to give hints to the query optimizer about what indexes to use. That's the two reasons you want to give it a name.
In shell, how do we see what indexes are? Like we have show DB for the databases. Will we show indexes?
I think it's something like that. I believe it's like DB products.show indexes, something like that.
Okay.
So there is a shell command for it, but I don't remember it offhand. So far we've talked about indexes kind of in general. We talked about some tips about what indexes you should create, and we started talking about text indexes. So as you saw, there's a few different ways you can create it. Typically, the best way to create an index is going to be as a wildcard index, as you saw here with the $***. You will notice the quotes around those. That is mandatory, because otherwise it's not a valid identifier in JavaScript. So that's why we have to put those there. But that's typically all you need to know to create an index. Is you just say, hey, it's a wildcard index everything, make it a text index, and set the name as text index. So most of the times that's really all you need to do. To index those tables that really make sense to index. So as we were talking previously, that would be things like products, that'd be things like reviews, that'd be things like users. It's not going to be every table, because not every table has textual data, but most tables do. So it's going to be a good sizable percentage of your tables. Usually at least half of your tables have some text data. So those should have a text index. So in this, creating this index is necessary in order to be able to perform a text search, which we'll talk about in a minute. You cannot perform a text search if you haven't first created a text index for that table, for that collection, sorry. So it's also, there's another thing you can do when you're creating those indexes. With the text index, you can also specify something called a weight. Now, when you do a text search, it basically returns all of the elements, all of the documents that contain those words that you enter. So if I say chicken, it will give me back all the documents with chicken in it. If I say chicken thigh, it will give me all the documents that have chicken, thigh, or both in them. But it will return those search results with what we call a score. And that score is a measure of how relevant or how close it is to what I asked to search for. So that score is, based on, does that document contain the search term, and how many copies of that search term does it contain. So that score determines the relevance, that relevance of that document. So for a text index, you can, by default, all the columns of the indexes are weighted the same. But oftentimes you may want to change that weight to be different on a per field basis. So maybe certain fields have a higher significance or more important than other fields. So they can have more weight in that score. And basically for each of those columns, those fields that come back with a match, you'll say take the score of that match times the number of matches times the weight, and then you sum up the results. So the weight is basically a multiplier for the score. The default weight for every field is going to be 1. So everything's weighted the same way. If I want to say double the weight, then it would be set it to 2. If I wanted to say set it to 4, that multiply it by 4. If I want to cut it in half, well, I multiply it by 0.5. So that way, just by setting that number, I can increase or decrease how important that field is to the text search. So to specify those weights, what I'm going to do is I'm going to specify the weights option when I call create index. So in there I have to say, this field has this weight, this field has that weight. Do be careful about how you choose the weights because they can potentially cause it to be either, it may end up needing to reindex the collection, or because maybe you chose the wrong weight, you might have to say, well, let's throw the index away and create a new one. So you do want to be a little bit cautious as you're creating those weights. To be something that's going to be more future proofed is probably not going to change down the line. So for example, what this might look like, let's say I'm again indexing the products. I may want to give a different weight to different fields of that product. So for instance, I might want to weight the description of that product as more important than the name, or the keywords more important than the name, or vice versa, things like that. So in this example, I'm giving the description a weight of 10 and the keywords a weight of 5. So what that means is, and you can see this is in the second argument, so this is the options object, is this whole thing. So that options has a name and it has weights. And remember that any field that I don't specify a weight for is going to have a weight of 1. So in this example, I'm giving the description a weight of 10, keywords a weight of 5, a name of weight of 1, and then all other fields that have string content are also going to get a weight of 1. So what that means is that a match on the description, for instance, is 10 times more important than a match on the name. And a match on a keyword is 5 times more important than a match on the name. Does that make sense?
Yep.
So that can be really helpful to make sure that you actually get relevant results back. There's not a really hard science about knowing what those weights are. It's really something you have to do with trial and error, and really depends on what you're building. But it can give you much better search results if you just play around with those weights. It can also discourage certain behaviors, like because here it says that the description and the keywords are more valuable. That means that you're less incentivized to try to put a bunch of keywords into your name, because the name is not as important. So putting more keywords that you think the user is going to search for into the description of the product will put it higher up in the search results than changing the name. And keywords, they usually should be something that's weighted a little bit higher, because those are typically sort of hand selected for the product at hand. So typically keywords, if nothing else, is something you probably want to weight higher than the other parts of that product or whatever it may be. Because they're usually more relevant. Let's say, if I was thinking about a blog, the keywords are probably more relevant than even maybe the text of the blog itself, because the keywords give a better indication probably of what's in there than the name of the article or the body of the article does. So we've looked at a few of those options we can set. Namely, we looked at setting the name of the index. We looked at setting some weights. Those weights are only available for text indexes. And we also looked at setting an index to unique as true. There are a few other properties that I just want to call to your attention that you can set as options. So we talked about unique. Setting unique and true says that whatever there is indexed, whether it be a single column, single field, or a combination of fields in the case of a composite index, that those cannot have duplicate values. Okay, so that's what that is. A sparse index says that you only want to contain, you only want to index things that actually have a value. And the place where you use this is if that field that you're indexing is often null. So if you may say, maybe you have some system where you have the quantity in stock on your products, but most of those products don't track how many you have in stock. Well, that would be a good place for sparse, because then you're only going to index the ones where that field is actually set. So a sparse index saves you a bit on memory and updates, because it doesn't save null values, whereas other indexes do save null values. Another kind of interesting sort of option you can set is something called TTL, or time to live. And time to live is for data that you're going to expire after a relatively short amount of time. So if you set time to live, then that document is going to go away automatically after a certain amount of time. So that's for data that you don't, for whatever reason, want to persist long term. So that may be codes for maybe resetting your email address, or changing your email address, resetting a forgotten password, other things like that. Maybe you have images or things like Snapchat, where you upload the image and then after time it goes away, or stories, things like that, where it's permanently gone. Maybe you have time series data where you only need to keep the last 2 weeks to a month of data. Well, you might give that a time to live, so it automatically deletes itself after a certain amount of time. Similarly with logs, maybe you're storing some sort of logging data in the database. That would be things where you would say, I want this to expire after a certain amount of time. So you can use that to automatically delete data, basically. You schedule it for deletion by setting time to live on the index. Okay, so most of your tables, you probably won't have that, but I want to make sure that you know that it's there, because it is a very useful thing to know about when you run into those sort of data, because you probably will run into those data in at least one of the applications you build in the industry, where you have some data you want to save in the database, but you don't want to keep it forever. So that can be very helpful. Next up is the name of the index. We looked at that already. There is a background option. You can set that to true or false. That used to be a way to kind of say, build and update the database, the index in the background, rather than blocking the user while that's happening. As it turns out, in MongoDB 4.2, this has been deprecated. So any newer version, 4.2 or later, it actually doesn't matter. It completely ignores the background setting, because it now always does the efficient version for the index. So it's always optimized. So it doesn't matter if you set it to background or not. It's going to run it in the background. Partial filter expression you can set if you say you only want to index part of the database. So maybe for whatever reason you only want to index some of the documents, then you could create an index just for that, and you specify the partial filter expression to say, well, what things do you want to filter and which things do you not want to filter. A wildcard projection allows you to say, there are certain fields that you don't want to index, that you want to exclude from the index. So I might say, well, I want to index everything except the price. So in the wildcard projection, you can say, well, you can specify what those columns, those fields are that you don't want to index. Weights we talked about for text indexes. Expire after seconds, it goes with that TTL setting. So you set TTL to true, and then you set expire after seconds, and that says how long do you want to keep around that document before it expires. So if I say TTL is true, expire after 60 seconds, well, then it would delete that record automatically after a minute. Okay. I do believe there are some additional options that I didn't mention on there, but those are really the only ones you'll need to know about for this course. And most of those you won't use as much. I would say the most useful thing in there is going to be your unique flag and the name. We talked about weights, that's helpful as well, but the biggest two in there are the unique and the name flags options. So now let's talk about how you actually do the text search. So MongoDB supports query operations that perform a text search on string content. In order to perform that text search, you need to use both a text index and the $text operator. So there's basically 3 steps to do a typical text search. The first one is to create the text index, which we just talked about. And then the next step is to say, use that text operator in your query. You can kind of think of that is basically falls into your where clause. So you would either be into find or the aggregate pipeline, which we're going to talk about in a minute. And then finally, we'll typically use the meta operator to sort the results based on their score, based on how relevant they are to the keywords that you entered. Okay, so that's the basic 3 steps that we need to do to perform any sort of text search. We have to create that text index, we have to use the text operator, and we have to sort them based on their relevance. Now, that text index, obviously, we only create that once. You don't need to create a text index every time the user hits search on the UI, but it has to be there in order for the text to work. If you try to use the text operator without a text index, it will complain, it will fail, it will tell you have to have a text index. Okay?
I got a question question. I don't know if you covered this already, but say we change the nature of what our index is like we'll add weights or whatever. All right, we created it before. So within shell, does it just override it if we give it the same name?
It doesn't override it. You have to delete it and recreate it.
Okay.
Yeah. Indexes are never overwritten. That's true with basically any database. If you want to change the database, if you want to change an index in any way, you have to completely delete the index and recreate it from scratch.
Okay. So when we do a demo, if you can show that, because I can see where we don't have experience with this, we have to go through that the process of create it doesn't work. All right, got to delete it, try again. All right, delete, create, delete. So that would be one of the first things I want to learn how to do.
It's really not that hard. So I think DB use samples and DB, I guess, show collections.
It's just show collections, show space collections.
Oh. So I've got an inventory collection, so let me see what's in there. db find, or db.inventory.find. So there's everything that's in that collection right now. If I wanted to index it, I would say db inventory, and let's give it a full text index. So create index. And then, so let's say boop, boop, boo, index everything. It's a text index. And we're going to give that a name of text indexes. Name text index. Okay, so that index is created. I think it's show indexes now. Look that up real quick. MongoDB show indexes. Oh, get indexes is the name of it. Okay, I was close. So get indexes. There we can see. So this, at the moment, appears to have a few different indexes. So it's got an index on the ID, it's got an index on the quantity, and it has that full text index, which I created. Now you'll notice that, for instance, the quantity one that I created, notice what the name is. That was the default generated name. So I didn't specify the name there. It created it as quantity one. So if I want to delete the index, I need to use that name. So if I try to create the index again, just as is, and say maybe let's call this text index 2, see it's going to say already exists. There's already a text index with a different name. There's already one there. If I give it the same name, either way it's going to give me, oh, well that went through. Interesting. Let's say I specify weights, because I do believe it should give me an error. So what do I want to give some weight? Maybe let's give the type some extra weight. So type has a weight of 2. There we go. So you can see that it says the index with name text index already exists, but with different options. See that? So I can't just recreate the index. I have to delete the index first. Paul, do you see that?
Yeah, I'm looking at that whole object there.
Mm-hmm.
So we got one called text index 2, one called text index, and then
There's only one. No. If I go back to get indexes, you'll see that there's only one called text index. When I tried to create text index 2, it failed.
because it's asking for the same criteria.
It's asking, well, because it's another full text index. Remember, you can only create one.
Right.
So
you're going to delete this one now.
Right. So even if I had said, let's say I hadn't supplied any of those options, and I said, let's just say, let's index the name, and there, it's going to tell me that there's a conflict, basically because there's already a text index there.
Okay, so any error thrown there is probably because it already exists.
Yeah. So I can't create that one because I have to delete the one that's already there. So if I remember right, it's just delete index, and then you just specify the name of the index. So the name of the index here is text index. Delete index. Is it drop index? Yeah, it's drop index. So I tell it to drop the index, and now I can recreate the index. So let's create it with those weights, weight of 2 for the type, and I can look at the indexes again using get indexes, and we'll see the weights in there now. So typically you have to, if you want to change, so anytime you want to change the index, you have to drop it and then create it again.
Okay, thank you.
Okay. So index is created. We can now use the text operator in our find, and then we'll use the meta operator in our score, in our search, in our sort, to actually sort the results by that. Okay. So normally when we're doing a find, remember we'd usually put in the name of the column the name of the field that we want to filter by. So for instance, we might put in the price or the name or the category, etc. In here, instead of the name of a property, we use the $ text operator. So in the place where you would use the name of a field, effectively the name of the field is $text. So that will search everything that you've indexed with the text index. So $text, inside of that you have to then specify what your search is. So use $search here for that. So $text, $search, and then you say this is the text that I'm looking for. So here we're looking for products that contain red, leather, and boots. So it'll actually return any products that have at least one of those words. If it has red, it will get returned. If it has leather, it will get returned. If it has boots, it'll get returned. What happens though is the more words it matches, the higher the score is going to be. So if it matches all three, it's going to have a higher score than if it just matches one of those words. But it doesn't have to match all three of those words. It just has to match at least one. So that's where the score becomes really important. If you don't sort the results by score, you don't really get relevant results. If you're just sorting the results by the name of the product, the user is not going to have a good experience. So we need to make sure we sort it by the score. We can also do things like, say we want to search for products that don't contain a word. You can just put a dash in front of this. So boots dash fox or dash faux will mean it doesn't contain anything with faux. So this would say, don't give me things with faux leather, right? give me boots, but not ones that have faux leather. So we can specify things like that using the dash.
That's interesting. There, you got the quotes.
Mm-hmm.
Well, okay, all right, that makes sense. All right, I understand.
So then to sort the results, we're going to then use that meta operator. And the basic way that you do this, you're going to then say add to project. Project adds or removes columns from your results, from your result set. So what we need to do is basically add to this virtual column, which is the text score. So we're going to say project, and we're going to add in a column named relevance. This can actually be named anything. I could say this is score. I could say this is relevance. I could say this is text score. I could say this is pony or unicorn. It doesn't really matter. But I would call this relevance because that kind of makes the most sense. Score is also a common one, so take your pick. But that's the name of the column that will be added. It obviously needs to be different than like a column that you already have. So if I call it score, that would override another column that I have named score. So that wouldn't be great for like a game thing where you have leaderboards and their score is in there, or things like that. But so relevance is usually one that's not used, so that's good. That's where I would use relevance. So relevance, I'm going to then give it the meta operator here, meta text score. So then that creates or adds a relevance field to the results that come back, and that contains the score. And as it turns out, just doing this will go ahead and sort it by, this will go ahead and actually sort it by the score as well. Okay. Any questions on text search?
I'm good.
Okay. So this is basically your start to how you implement this. What we want to talk about next is going to be a little bit more complicated, and this is more than, we haven't touched on this stuff yet. So all of this is going to be new. So we're going to talk about something called an aggregation pipeline, and this is specific to Mongo. But this is basically the way that you write select statements in Mongo. So aggregation pipelines are modeled after this idea of data processing pipelines, where you do one thing and then hand it off to the next piece and then hand it off to a next piece. You kind of think of it as an assembly line where everything's kind of coming in, and you have different stages that it goes through. And each of these stages are going to do some sort of transformation on the array of documents that comes in. So whatever comes into that stage will come out a different way. But each of these stages are connected to each other. So the input, the first stage takes all of the documents in the collection, passes things to the next stage. That stage takes all of the inputs from the previous stage, passes on to the next stage, on and on and on and on. So for instance, this is if you wanted to do grouping like you do in SQL, the way to do grouping is with an aggregation pipeline. So for instance here, let's say we want to group the orders by the customer ID and sum up the total costs for each of those orders. So the way I'm going to run this through, I'm going to say db.collection orders aggregate, and you'll notice I'm now switching over to the Node syntax, because this is typically you can write this in the shell and test it in the shell, but these are typically things that we're actually going to do in Node from here on. So we're getting closer to code. So in there, instead of calling find or instead of calling find one, I call aggregate, and aggregate then takes an array of stages. So aggregate takes an array of stages. So here I'm passing it 2 stages. The first stage is a match stage, and the second one is a group stage. You see that with those operators here?
Yeah.
So that operator determines what kind of stage it is. So a match stage is like your where clause. So we say I only want the orders where the status is A. Whatever A means, I only want the ones with the status of A. And then I'm going to group after I've done that, I'm then going to group all the orders that remain and say, well, let's group them by the customer ID. And you'll notice there's kind of an interesting syntax happening here. This $sign in here, $sign customer ID, that $sign means that it's a field in the input collection of documents. So basically, I'm almost renaming the customer ID column to _ID. Okay, so it was previously named customer ID on the orders. That's now going to be the primary key for the grouped results. So that _ID is what you're grouping by. So we're grouping by the customer ID. So now the records that come out, they'll have a column named _ID, but that will be the customer ID, or what originally was the customer ID. And then we're also specifying that the results of this grouping have another column named total, and that total is the sum of all the amount columns in the orders. So take all the orders for each customer, add up their amounts, and that's the total. So the result of this stage will be a document that just will be documents that just have an ID and a total, and that's the only thing that will be there. So we've got a matching stage and we've got a grouping stage. And so when you specify these stages, they always happen in the order that you specify them. They're always going to be executed in the order that you specify them. That's different than the world of SQL. So if I write a select statement, is that select statement executed from top to bottom? If you remember, it's not, right? In SQL, your select statements are not executed in the order that you write them. In fact, oftentimes the query optimizer will decide what the most efficient way to execute it is. With an aggregate pipeline in Mongo, it will execute it in the order you tell it to execute. So that does mean that sometimes you can get better performance if you change the order of your stages. It also means that you can get different results if you change the order of your stages. Okay? Because the order that you specify is important. So looking at maybe a video diagramming this pipeline, they're going to kind of go through some example orders, push that through, and you can see what happens with the different stages. So we take some data in, which is our orders. We perform the match, and you can see, I don't know if this paused. You can see from there that we lost this document here that did not match because it wasn't a status of A. And then we grouped it down from here till finally we've got, let me get back to the end here. So you do a match, and then we do the group. And I guess that didn't pause it. There we go. That's what I want to do. So we do the grouping, and then in the end, you see that we have 2 documents, right? So we grouped by the customer ID. So you can see each of these have a customer ID column. Notice that these first two documents have the same customer ID. You see that? So they're going to get grouped together. So A123, A123. So these will both be grouped down to this document here because they have that same customer ID, and then we'll add up the amounts. So 500 plus 250 is 750, and then this one finally here, B212, it doesn't have any, there's no other records with the same customer ID, so it just comes out directly with the customer ID, and we add those up. Well, 200 plus nothing is 200. Cool?
Yeah.
Now, if we had changed the order of these, right? So let's say we had done the grouping and then the matching. We'll notice that these columns, notice that this doesn't have any sort of status, right? So for instance, if I tried to do the match out here, I would actually get no results because none of them have a status. I also would, if I tried to do something after this point, this would have been grouped into here, and the total would have, if we had done the grouping first, that total would have been not 750 but 1050 because you'd have an extra 300 in there. So again, your order of your stages really matters. Typically, you're going to do your match stages early. Think of your match stage kind of as your where clause. It's typically the first thing you're going to do, but it doesn't have to be, but often it is for efficiency's sake. So in that example, I kind of went over this already. The first stage filters the documents by the status field. That second group stage is grouping by the customer ID and then computing the sum of the amount for each customer. So an aggregation pipeline in general is going to consist of stages. Each stage transforms the documents as they pass through the pipeline. Pipeline stages do not need to produce one output document for every input document. So, for example, some stages might generate new documents, and other stages might filter out some documents. So, for instance, if we're looking at this, that match stage reduced the number of documents that are going through the pipeline. And group actually collapsed them down as well and basically produced new documents, although it ended up producing fewer documents. Okay. Pipeline stages can actually appear multiple times in a pipeline. So for instance, you may have more than one match stage. You might need to do matching at one point early in the pipeline and then another match later in the pipeline. Depending on how you set things up. Because, for instance, you may not have the data to do some of the matching early on. You may need to do some calculations before you can do that matching. Okay? So there's a long list of stages that you can add to your pipeline. Okay? The first one is, and we'll quickly go over these, what these are, and then I'll give some examples for each of them. So, for instance, the match stage is used to filter out input documents by specifying conditions. So, like we said, the status has to be A, or we might say that the price has to be less than $100. Sorting is used to sort the input documents by a particular set of fields. Order of that obviously matters, so you might sort by the first name and then the last name, or you could sort by last name, first name. Both of those will give you two different orderings. Then you can have a group stage, which we just looked at, which collapses or groups documents together based on a specific expression. We can have a lookup, which performs a left outer join to a collection in the same database. It's worth noting that lookup only does a left join. It is not possible in Mongo to do a right join, an inner join, or a full join. Those do not exist. You only get a left join. It's the only kind of join you have is a left join. As it turns out, that's basically the only one you need. With the way that things are structured, because you have nested documents, for instance, the only one you will ever need is the left join. Okay?
Yep.
So you will never need to do an inner join. You will never need to do a right join or a full join, has been my experience. In reality, in relational databases, it's pretty much most of the time it's going to fall into an inner join or a left join, and usually a left join is oftentimes a better pick than an inner. And most of the times you can rewrite queries that would be right or full as something else. Basically what happens is, because you have nested documents and because you can have arrays inside of your nested inside of your documents, that's how you get out of needing to do right and full joins. Because a lot of the reasons that you need right and full joins in relational databases is because of needing to model many-to-one and many-to-many relationships in a sort of non-intuitive way. But because you can do that with arrays, you can nest arrays, you end up not needing those right joins. So you can do a lookup, which is basically a left join. You can do count. A count stage just counts all of the documents that are coming into that stage and gives you out the count. Nothing else.
These are in no particular order, or are those in some sort of order?
These are not particularly in any particular order, I'd say.
Okay.
They're roughly in order of usefulness, probably is the best way I would say. So match, you're going to use basically all the time. Sort, you use most of the time as well, about as much as match, because pretty much every aggregation pipeline should have a sort. Group is a little bit more rare than that. Lookup is probably more common than group, but not as common as match and sort, because not everything needs a lookup, but a lot of things do. And then count is kind of a rare one, but is useful for things if you need to figure out the count for different things. Let's see, yeah. If you for a reason just need to get the count, that one comes up, but that's not as useful. The next ones up are skip. Skip is kind of like, you remember we had skip in Flex, or sorry, not Flex, Connects. So we could say, I want to skip a certain number of documents. So I could say skip the first 5 documents, first 10 documents, oftentimes used in paging. Limit, similar thing. I can say I only want to get up to such and such documents. Again, useful in paging. Project allows us to pass only certain fields to the next stage. So I might want to say I don't want all of the data from the documents, I only want some of them. Or I may want to add additional columns, add additional data to the documents. I can do that there. I can either remove data or I can add data using project. Project is probably the most complicated one of these stages, to be honest. Set allows us to add new fields to the input documents, and unset allows us to remove fields from the input documents. Set and unset, both of those can be done with a project. It just depends. Sometimes sometimes it's a little bit easier syntax to write it as a set. Sometimes it's easier syntax to write it as an unset, and sometimes it's easier to write it as a project. So it really depends on what particular use case is, which of those three you should use. But they work very similarly. Other stages you have are GeoNear. So GeoNear allows you to sort the documents by the geographic distance to a particular point. So you might say, well, give me all of the Walmart locations that are, nearest to me. So I would use a GeoNear to sort it by the distances. Sample allows me to randomly select a number of documents from the search results, from the things that are coming in as input. So maybe I want to take, for instance, 20 random documents. I could say, sample 20 documents. So that's really useful for things where you do need randomness, especially for things like games, or if you're doing statistical models. Sample is really helpful. Sample can also be good for things like suggestions. Like YouTube has a suggestion that gives you, here's videos you might be interested in. Well, at some point there, you need to make something. You need to say, here's the best ones. We'll randomly pick some. So that can be helpful for suggestion algorithms as well. There's another one which is kind of more statistically oriented, just like sample is a little bit more statistically oriented, which is bucket, and that categorizes your input documents into buckets. So that's good for things like histograms, which would be like a chart of here's the number of things that fall into these different categories. So that can be helpful because you can kind of specify, every bucket is 100 wide, or you can also ask it to automatically figure out those buckets. Bucket's helpful. We won't really talk about it here, but I wanted to at least mention that it's there. Either way, this list is not comprehensive because there are so many different stages that are available. So I'd really ask and suggest that you should read the documentation on the aggregation pipeline stages to see a full explanation of every one of these stages, the ones that you're going to use, to find out more about them, as well as to find out other ones that are available. If we tried to go through every single one of these, we would be here for a very long time because there are a lot. There are a lot of stages that you can use. But that's really, really good that there are so many stages. So let's talk about just some of those most commonly used ones. So the match stage, as I said, is used to filter out input documents by specific conditions. It's basically like your where clause. So you're going to say match and then your conditions. And we kind of talked about this with the find. It's the same sort of syntax as find. So match, and then here I might say the author is Dave. So only give me documents where the author is Dave, or only give me ones where the price is less than or equal to 100, or let's do a full text search and go look for leather boots. So I can use the full text search here in a match stage in an aggregation pipeline. Cool? A general optimization tip is you should place the match stage as early as possible in the pipeline to reduce the amount of data that the rest of the pipeline has to process. So usually the match stage should be the very first stage that gets executed.
Question, author. If I want to find Dave or David, would I put a percent in place of the E?
No, what you would do is use the in operator, and you would say in Dave or David.
So there's $match colon and then author colon and then
author colon, and then you're going to start a new object and you're going to say $in colon array Dave David.
Okay. Yeah, I've been getting the syntax. I hear you. But just seeing the syntax.
Yeah.
That's all right. We can get to it later.
Yeah. So you see how this LTE operator is here? You basically put the in operator there. So in, and there'd be an array of Dave and David. No, there is no such, like, the like operator that exists in SQL does not exist in Mongo. There is no such thing as a like. But that's okay, because the like operator is actually very inefficient in relational databases. It's not an efficient thing to do, and it usually doesn't give you back good results anyway, to be perfectly blunt. So that's an okay thing that it doesn't exist, largely, because it's usually better to just do a text search rather than do a like.
Yeah, the closest thing is the in operator then.
Mm-hmm. But the in would be the way you would do that. The thing there is then you need to specify from the user's perspective. Somehow you have to specify multiple things, right? So you have to be able to take it from the user as an array, not as a single string, effectively. And you might do that by having spaces in the field. You might have that by doing commas in the field. But you basically end up having to split the things that the user typed in. So the next up is the sort stage. And the sort stage basically has this syntax. It starts with $sort. And then you say which fields you want to sort by. So if I want to sort by the author ascending, I would say author 1. If I want to sort by the price descending, so like the highest price item down to the cheapest item, that would be price -1, vice versa. Price 1 would be ascending. I can, just like we saw with previous sorting, I can specify more than one column here. So I could sort by the author, the name, and the price. I could sort by multiple of those. Usually that comes up if you're sorting by last name and first name. You would sort by both of those in whichever order you want them to be, either last name first or first name first. And then we can finally do, like we talked about with doing the text search, I can also sort by their relevance score. So here I would say, let's sort by the score and the meta text score. So this would sort by the relevance to whatever text search I performed. This only works as long as you had a text search previously. So you had a match stage with text search previously. It's generally good to put the so the sort stage has some rules about where you can put it in terms of being able to take advantage of an index to sort. If it's preceded by project, unwind, or group, then sort cannot use an index. Otherwise, it can use an index. So that's worth noting. And that's not just if it's directly preceded. If any point before the sort there is either of those three things, then it has to do it inefficiently. It has to do the sort manually. Can't use the index for that. Which oftentimes means, project often happens in there, and it's not unusual for the project to necessarily need to, it's not unusual for the project to need to happen before the sort. That does mean that a lot of times you can't necessarily take advantage of the index, or you have to jump through some hoops in order to move those things around. The group stage, as we saw previously, will allow us to group things into sort of collapse things into groups. So it always starts with the group operator, and then you have to specify _ID. Regardless of how you're grouping it, it's always going to produce it as _ID, even if that's not an object ID that you're sorting it by. So for instance, here we're grouping it by category, or we could group it by the product ID. So we can group this a bunch of different ways. So for instance, here, I believe that these two, let's say we're grouping our products by category. I might say, well, let's group it by category and then give me the total stock. So add up the stock, sum it up. That will give me how many of those items that we have in stock for that particular category. So I might group it. I can see, well, boots, we've got 500 boots available. And hats, we have 200 boots, 200 hats available, etc. I could say, well, let's take the minimum. So I could say, let's take the minimum price. That gives me the cheapest price in each category. There's a lot of operators actually that you can use here, a lot more than what we call accumulators that you can use as this. So definitely look deeper into the documentation. You can follow that here to see what some of those accumulators are, but there's a min, a max, average, sum. There's quite a few that you can use when you're using a group by stage. So those are two ways I could potentially group products. Let's say I'm grouping reviews. Well, maybe I want to group the reviews by the product that's being reviewed. I might then take the average rating. So I'd say average of the rating. So that will give me the average rating for each product. Or I might say, well, give me the first review for each product. So this might give me the review text for whatever the first review was, based on a product by product basis. So you have a bunch of operators that you can use, and you can actually combine these. So I could say I want the min, the max, and the average. I could get all three of those. I just specified that out as additional fields. Next up would be the lookup stage, which I mentioned. The lookup stage does a left outer join, and it's to a collection in the same database. So I might say let's join the products to the reviews. So the basic syntax for that is I want to start with $lookup, and then I need to specify a few options as far as how that's going to work out. So from says which collection do I want to join in. Local field is the field in terms of the input that I want to use in the join, and that's kind of where you would put that in on. And we're going to say local field equals basically equals the foreign field. And then finally, in the output, I need to say, well, what do I want that array of things that were joined in, where do I want that to go? So as would be the name of the resulting field in the output. So basically, this is going to add a new array field whose elements are the ones that we joined in.
Yeah, I noticed you don't specify products in there. It's kind of like you know that you're at products already, so you just use the foreign table name and that's it. Right,
because that's basically how you specify the input. So when I'm starting this out, I'm going to say db dot collection products dot aggregate. So the input table is basically specified before you even call the aggregate function. So this is starting with whatever the input to this stage is, and then doing a lookup to the foreign table. So let's say we're looking at products. Well, products have a local field of _ID. Then I want to join that to the foreign field, which is product ID. So join the products ID to product ID over there, and then I'm going to save that as reviews. So now when I get back my results, that would be basically an array of products, and each of those products has an array of the reviews for the product. That's what this is producing. Similarly, if I want to say, let's take a course, and I want to go find all my students that are in that course, I might have a field in that course that's called student IDs. So that'd be an array of student IDs. And then I want to join that to the _ID field in students and save that as students. So now my output, my courses have an array of students, and that array contains everything from the students collection.
Okay. Does the order matter? Could local field become before foreign field? Is that
Yeah, it doesn't matter. You can put these 4 in any order you want.
And let's say you wanted to do another left outer join to something.
Mm-hmm.
How would you do that?
That would be another lookup stage.
So after the final curly brace, it would be $sign lookup.
So you put a comma.
Okay, comma,
and then add another stage.
Okay, and it'll throw an error if you don't link it up the right way. So you would have to have your local field would then be. What are we doing here?
Whatever's in your input. So
well, you're starting off with products, and then you.
So this would be courses. So for instance, I could join the students in. I could also join the instructor in. So I might join the students in, but then I might also say, well, from instructors, foreign field is ID, local field is instructor ID, and call that instructors. So I could join in the instructors in there as well, or join in the tests, or all sorts of things like that.
Okay, so it doesn't necessarily need to be table 1 to table 2, table 2 to table 3. It could be table 1 to table 2, table 1 to table 3, all in the same query.
Yeah. That's usually what it happens. That's usually what you have. Is you say you start with the first table and you join in the other pieces of data that you need from other tables.
Or it might not be possible because there may not be that foreign field that's table 1 has that's in table 2 or table 3. You have to go from 1, 2 to 3, not from.
If you have to do that, then you should. If you have to do that, then generally that's a sign that you should change the way that your schema is. That generally means that there's data that you probably should make a copy of, so that you don't have to go through another layer, or it means that maybe you don't need to do that join. Maybe there's a better way to do that. But usually I would say if you need to say table 1 goes to table 2 goes to table 3, probably table 1 or table 2 is missing some data that should have been there, so that you didn't have to go to table 3 that way.
Yeah, I'm trying to think like a practical example, like if we're talking about the travel website. Maybe you have the users say their homepage, like here's my name, here's my email, here's where I'm from, and here are my reviews. So you would have the places. Maybe I'm thinking about this too hard. I don't know. I'll save it. It's a sidebar. It's gonna take a while.
Yeah. But anyway, the point is, this is how you do a left join. And one of the things that you'll notice in there, unlike left joins and all sorts of joins that you have in relational database, typically when you do a join, that changes the number of results you get back, right? So I might do an inner join, and I started with maybe I had 3 records, and now after my inner join I have 100 records, right? Or it could be vice versa. I could start with 100 records, do an inner join, and now I'm down to 3. So in a relational database sense, anytime I do a join, that can change the number of records that I'm working with, right? Because of how lookup works, lookup never changes the number of documents that you have in your result set that you're working with. Because those results always get pulled into an array, that array may have no records, that may array have 1 record, that array may have 10 records that are connected. It doesn't change the number of records that you're working with, which is huge. That makes things so much easier. That's part of where some of the queries that we were looking at, like getting the average rating of a product, is actually really hard, because once I group in the ratings, now I have a bunch more records, typically, and then I have to group that back down to a smaller set of things, right? So So this actually is a lot easier because it doesn't change the number of records you're working with. Count is pretty simple. The count stage, you just tell it, well, what's the name of you want the output to be? So if I say $count, I will get a column named count with 4. If I said size here or length, this would be size. Then I'd say size 4. So this is just the name of whatever the output wants to be. And count, in contrast to most of the other stages, typically give you an array of results back to the next stage. It just gives you a single document, which is the number of records that were fed into it. Skip, pretty simple. You just say skip and the number you want to skip. So here I'm skipping the first 5 records. Limit, similar way. I just say how many records do I want to have at most. So this will say limit it to 5 results. Or I could say limit it to 100 results or 1,000 results or whatever. All you'd have to do is just specify a number there because that's all the information it needs. So typically your skip and your limit stages, those are going to be close to the end and usually the last 2 stages that you do. Not always, but usually they're pretty close to the end. Project also tends to be pretty far to the end. That one is one of the ones that might be after. That one sometimes is even after limit, depending on what you're doing. But the whole point of project is to either add or remove fields to the result. So project is kind of weird because it can take a bunch of different forms. So, and it works differently depending on how you specify it. So in terms of project, by default, you'll always get the _ID coming through. So if you want to specifically remove the primary key from the results, you have to specifically suppress it. So the way I do that is with a project, and I say _ID is 0 or false. Typically we use 0. So I'll say _ID is 0. That means I don't want to see the primary key. Similarly, I can include and exclude fields. So I can say, what's the field name 0, that's to exclude the field, or field name 1 would be, I want to include the field. You can also use expressions there to potentially add or replace an existing field. So for instance, we saw that previously with project, I added the relevance field on. So some examples of how this project stage might look. I might say project name 1, description 1. Well, what this is going to produce is a set of results that only have name and description. Nothing else. It's throwing everything else away because those are the only 2 I've specified. Okay? So if I say all ones, actually it's going to have I forgot to mention, it's going to have the ID as well. So this would actually have ID, _ID, name, and description. Because we haven't explicitly excluded it. So if you just have ones, you're saying these are the only columns I want. Questions? Throat's dry. So this is saying I just want the name and description. You can kind of think of this as your select clause, where I'm saying these are the only columns I want as my result. I might add in the relevance. So here I'm saying score is meta text score. So that will give me how relevant that search result is. So this is going to produce those 4, the ID plus those 3. I might also say the reverse and say I want to specifically exclude certain columns. So I could say, let's give me everything except sizes, colors, and images. See that? So you can specify what you want to include, or you can specify what you want to exclude. So this is only these two columns, and this is everything except sizes, colors, and images. If I want to then use the underscore ID to suppress the ID, sort of a similar syntax, but it's worth mentioning. You still have the suppression or inclusion option. So here we're saying don't include the ID, but do include username and email. The result will be just username and email. Opposed to if I say let's exclude the ID and exclude the password and exclude password hash, well, this would have everything except those three columns. Questions? Project stage is kind of the weird one out because it works differently depending on if you're including column or excluding columns. And there's not a hard and fast rule about which of these you should use. Sometimes you want to be very specific about which ones you include, and sometimes you're just trying to knock off one or two columns that you don't want to be in the result for privacy concerns or whatever else. Geo-near stage is fairly easy to specify. I want to mention it briefly just so you know how to use it. So geo-near says sort them by the distance to a specific point, and typically you would feed in there the current user's location. So the way you feed that in is it's the geo-near stage with options. There's a whole host of options you can pass in, but the basic sort of example would be, let's say it's near this point. So these are my latitude and longitude coordinates. We're going to say that the key is location. So the location is a field on the input documents. And then we're going to say put the distance to that into a field named distance. So that would give you results where it's like, okay, well, how far away are each of those things from this point, and sort them by the distance to that point. I can add other options here. So for instance, here I'm adding the max distance. So I'm saying don't give me anything that's farther than 100 meters away. And there's some additional options you can specify in there. So you can see the documentation for a lot more information and examples of that, all the different pipeline stages and how they work. There's a whole lot of examples there and available. I just wanted to present some of the simple examples so that you can kind of see it and know where to look as you're working through these types of queries. So let's kind of look at, what might I do if I'm trying to build an aggregation pipeline to search through products. Okay. So here's an example pipeline. Okay. And we can look through this and we'll see that it's got a few different stages. So I've got a match stage, which I'm filtering on a few different things. I'm doing a lookup, and you see, what table am I looking up? What table am I joining in?
Oh, was that a question?
That's a question.
Looks like ratings, huh?
Looks like ratings. So I'm starting with the products here, and then I'm joining in the ratings, right?
Yeah.
So I'm joining on the product ID, and you can kind of see that here, local field, it's underscore ID on the products table, it's product ID on the ratings table. So I'm joining in, that will give me an array of ratings for every product. And then I'm going to then use that immediately in the project stage. And that project stage, then I'm saying what columns I want to keep. And I'm doing a little bit of calculation in there as well. Come back to that. And then I've got a match stage. You'll notice I actually have two match stages. I have one match stage up here, and I've got another match stage down here. Reason being is this part of the match can't be done until later. I could have combined both of those match stages and put them down here. The reason I want to do the first match stage up first is because it's actually faster to do this matching first, because it produces less results that have to be worked with later. And then doing this again, this part has to be down here because of the way it's working. And then finally, I'm doing a sort. Okay, so you can kind of see, even here in a relatively common sort of aggregation pipeline, I have how many stages. How many stages do I have here?
Oh, looks like 6.
Okay. Why 6?
Match, lookup, projects, match, sort, collate.
Now, collation is not a stage.
Okay, did we talk about that, or?
We haven't yet. So notice where the square brackets are? Here and here. That's the end of the aggregation pipeline. So most of these methods in Mongo, if there's another argument after that, what is that usually? It's usually options. So this object here is some options. You with me?
Yeah.
So collation tells it how to deal with equality and range matches based on text. So by default, your matches are case sensitive. So the case would have to match exactly. What this collation that I'm setting here is to change it to a case insensitive search. Because I don't care if it's lowercase or uppercase, I want it to behave the same. So in the collation, I need to specify two things, the locale and the strength. The locale says basically what country and culture am I working with. So here I'm saying EN_US. EN is short for English. US is short for America, USA. So we're using the American English locale, and the strength 1 says to do it in case insensitive, basically. There's a bunch of different strengths. The default strength is 3, which is case sensitive. So what I'm doing there is basically just telling it to do a case insensitive search. Okay? Any questions on that collation?
No.
Okay.
Yeah, just a comment. It looks like a nightmare to try to feed in all the data, because that is a Mongo shell, right? That's how that would be. But if I'm feeding in, say, like greater than, equals to 10, 200, all that, that's, yes. Oh.
It's not really that hard. I've got an example of how you build this dynamically. But the gist of it is, here's what I'm ending up building as an example. I would generate this pipeline dynamically based on what the user enters. Okay. But we're not quite there yet, right? So the overall structure I want to show you is where these pieces fit in and what our goal is. Okay. So let's look at the match stage first. So the match stage is where we do our filtering. Okay. So the filtering here that I'm doing, well, I'm saying I only want products that are a category of boots. Okay. I'm only saying I want products that have a price that is greater than or equal to 10 and less than or equal to 200. So between 10 and 200. Okay. In reality, what we want these to be is these are probably going to be dynamic, right? The user's probably going to type in or pick the category from a drop-down, and this greater than or equal to, less than or equal, these are probably going to be things that user types into text fields. Okay? So they may or may not be there. They may have a different value. The next thing I have in here is $text. Remember, that's our text search. So we're also doing a keyword search and saying, I want products with the keywords red, leather, and boots. Okay? Questions on that match stage? So we're applying a bunch of filters. You see how those are kind of common? You see those in most online stores?
Yes.
So there's still a question of how do we build that? We'll get there. But basically, you have this match stage where you're going to put your filters. Okay. So then we've got the lookup stage. We kind of looked at this briefly. I'm then bringing in the ratings. I'm doing this, as I mentioned, I want to do the match first to reduce how much work. So that means, by doing this as the second step, I don't have to do a left join with anything that would have been filtered out anyway. So for instance, if I had swapped these two sets, then I would have had to look up on every product, including hats and belts and whatever other products I have to get all their ratings, even though in the end, I'm only cared about boots. So it's quite a bit faster to do the lookup second. Cool? The next thing I'm doing is the project. So in the project, I'm saying, remember with the one, I'm saying which columns I want to include. So anything I don't specify here will be excluded. So I want to say, give me back the name, the description, the price, the keywords, and the colors. Everything else is going to be, if there's any other columns or fields in the products collection, I'm going to ignore those fields. Okay. So for instance, I just added an array of ratings. I'm not including that. So that's actually going away. Okay. So this result won't actually have an array of ratings because I've not included it here. What I am including is some calculations using those ratings. So for instance, I'm saying, let's count the number of ratings. So I'm going to call this column rating count. And I'm going to say, well, let's take the size of that ratings array. So that gives me how many ratings have been placed, have been given for this product. I can take the average of all the ratings. So here I'm saying, let's go through that array of ratings and let's average the value field, which is where they're putting their value. Might be 1 to 5 stars or however you want to rate it, -1, +1, up, down, wherever you want to do that. It will take the average, and that was what we're getting here. And then we have the relevance, as we saw previously, because I'm doing that full text search up here. So I add those 3 columns to the result set. Okay. So the end result, I am, when I do lookup, I'm bringing in all these ratings, but then I don't actually keep all that data because that would be a lot of data, and I don't really want to see the individual ratings if I'm searching for products. I just want this aggregate information of how many ratings and what's the average. So then, I mentioned that there's 2 match stages. So I have a match here and a match here. In this match stage, I'm now filtering out anything that's rated low. So I'm saying rating average is greater than or equal to 3. So anything that has an average rating of less than 3 won't be included. So the reason I couldn't do this filter up here in the first match is because the rating average hasn't been calculated yet. Does that make sense?
Yep.
So I couldn't do this filter in that match. I needed to do it down here because it wasn't calculated yet. But as I mentioned just a minute ago, the reason why there's 2 is because if I took all this logic down here, then this query would take a lot longer because it wouldn't have the chance to filter out all the data at the beginning. So it's important to think about that. And sometimes like this, you will have more than one match. I have the filters that I can do before I do calculations, and then the filters I do after I do the calculations. And then finally, I'm sorting the products by their relevance in descending order. So the most relevant ones will become earlier up in the results. Okay? I hope you can see that's a very common sort of filter and query that you might run. If you look even just something like Amazon, these are very common filters of keywords and categories, price ranges. You want things that have a certain number of stars or more. That's all there. Okay? Okay. So how would you, let's say, a number of these values are probably going to come from the user. We'd want to write some sort of backend that will take those values from the user and build up this pipeline more dynamically. Okay? So let's start by thinking about what are the things in this query that should be user-entered values. What values should the user be providing? Be dynamic.
Well, the price, for one, that can be typed in or maybe drop down increments.
Okay. Yeah. So somehow the user is going to type that in. Are they typing in just this part or just that part? Or both?
It could be two fields where one would be, of course, you could make it where there is no price where they would interfere with each other, or maybe a drop down with a range or something. I don't know.
Right. So I would think about it this way. You've got a minimum price and a maximum price. Right? So they can enter a minimum price and a maximum price. What else? What else in here is user entered?
Category is a drop down.
Category is probably a drop down.
The search.
Okay, so this search string is going to be user entered. Is there anything else that's user entered?
Yeah, I'm thinking of like Amazon, the second match there where you want to see only products that have an average rating of 3 or better.
Yeah, so that might not be 3 or better. It might be 4 or better. Or they might just not put that in that match at all, right? They might want all the results.
Yeah, and, well, you could have a checkbox for any of the fields you want to include. But I think that's probably too much on the user. For UX there, just include them all. There's only, what was it, like 7 there? 8?
1, 2, 3, 4, 5.
Oh, I was just thinking name, description, keywords, colors, rating, count.
Right. Well, what? Yeah.
The user would see that, right?
We what?
The user would see that, right?
Yeah, they're gonna see. We're gonna expect to see all this stuff. 1, 2, 3, 4, 5, 6, 7, 8. That's not unusual to see all that information. In fact, there would probably be more because you'd have images you want to show.
What I meant by that is when we display that information, the user would just see it all, period. They wouldn't check what they wanted to see by utilizing a checkbox.
Yes, yeah. Typically, whatever's there in the project, the project and the lookup, those things are like they're hard coded in, right? So these are things could be user variable. Usually they're not. So the only things I need to filter in is that and the match. Oftentimes the sort would also be something that's user entered as well. They might choose how the results are sorted. Okay.
Yeah, I've seen that too, where you can sort things by price, by name, or by the relevance. I always wondered what that meant. Is that a MongoDB thing, or is that all? That's databases.
That's actually pretty much any time you're doing text search. It's basically what the standard name for it is relevance. So if you're doing even MySQL, remember, has a full text search, which we've used. That produces a score as well, a relevant score, or a text score. So that actually exists on most databases now. Okay. So if we think about that, grand total, we got about 6 inputs, right? So if I want to, let me get out of Mongo here, type in exit. Hey, Google, turn on the office lights. My lights turned off. So let's go into here, and I want to, can you see VS Code right now?
Yep.
Okay. So I've got an example project here. If you want to get this one yourself, that's in my example, it's the same repo that I've given you before. Just look under Unit 4, Examples. This is the MongoDB Examples project. So what I'm going to look under is, here I'm going to go to API and go to search, because I've got this search API here. Okay. And let's look at the browser. Let me pull that up in the browser so we can look at what this is producing. So API search. So my objective is, initially, if I go here, it's just going to fill in all 6 of those values with default things, first of all. And then as I start adding in additional pieces, it'll start using that to modify the query. So for instance, if I want to search for hats, I might say Q is equal to hats. So that will reduce anything that has the word hats in it, and you can see the relevant score on it there as well. Cool. Or if I wanted to say, let's see if I can get Lorem Ipsum to come up. Does Lorem come up? Maybe. There we go. So Lorem Ipsum, and you can see this one has a score of 5.5. Okay. So you kind of see what I'm starting to build up is a back end. So let's go back to the code. And so I've got this API module called search. And in this route, it's a get route because I'm getting data. I'm going to take in several different inputs. Okay. So Q is going to be my search term. It's my query. The reason I use that is that's actually used by several popular websites, including Google uses Q there, and I think that Amazon as well. So that's kind of a common name to have as your search terms, your keywords, but that could be called search, it could be called keywords, it could be called whatever, but I'm going to call it Q. Okay, so Q is my search terms. I'm going to get the category if you want to filter by category. So I could try that in the browser, for instance, here. Let's say category is equal to hats. And you can see what comes up is just going to be things that are hats. Let's try boots just to verify that works. So the category lets me specify which category I want. I can also specify which color I want. So I can say, well, I only want black boots, or, red or brown or whatever the color of my choice. Specify a color. I can specify a minimum price, a maximum price, and that minimum rating. Remember, we had that in the second match. You saw that? Yeah. So that's what goes there. I also have a place to specify sort by. So maybe I want to sort it by the name or sort it by the price, etc. So I can specify that in sort by. And then I've also got some paging in here. So I can specify which page do I want. By default, it's going to start with page 1. And I can specify how big I want the pages to be. By default, they're going to be 10 items per page. Okay? Now, you'll notice that some of these that are numbers, I need to go ahead and parse them as numbers because by default, they're going to come in as strings. Everything that you pull in from the query comes in as strings. So I need to parse this as a float, parse that as a float. These are all numbers. And then the page and the page sizes are both integers. If I don't do that parsing, then later on you will get errors because you have strings. And the aggregation pipeline in particular places expects there to be numbers. Okay? And not strings. It won't automatically convert them from strings to numbers for you. So let's think about the stages in here that are variable. So if I think about this match stage is variable. This match stage is variable, and this sort stage is variable, right? So if I think about that, one of the ways I can build that up is thinking about those as, well, variables. So maybe we start by building the match stage. So I'm going to start the match stage as being just empty object, to saying there are no filters. Does that follow?
Yeah.
So start by saying I want to get back everything. And then if you give me additional values, I will start using those values to filter the data. Okay? So for instance, if you give me a query, then I'm going to say, let's do a full text search. So I'm saying match stage dot text dot $text is equal to this object here. So I'm adding in what was previously no filters. I'm adding in a filter. Does that follow?
Yeah.
So I'm saying let's filter it. Let's put a text search in there to search by keyword. And then if you specify a category, I'll add a filter by category where I say, okay, categories has to be equal to the category that you entered. If you specify a color, then we're going to say colors is equal to the color you specified. And that actually works whether whether the products in question can only have one color or if they can have multiple colors, as long as the name of the property is colors. That actually works with an array of colors or a single string. And then I'm going to say, let's look at the min and the max price. So if you specify both min and max price, we're going to say, well, the price is greater than or equal to the min price and less than or equal to the max price. If you haven't specified both, then we'll go check, have you specified the min price? If you specified the min price, then put that in. And then finally, if you've only specified the max price, then we'll just say it's less than or equal to the max price. So does that make sense as far as how I'm building up that match stage dynamically? I'm using the fact that it takes an object and just building up that object. Questions?
Nope.
So dynamically, I'm building up that stage. And let's say now I want to build up the sort stage dynamically as well. Well, so we're going to start with sort stage is null. I don't know what the sort stage is going to be. And then let's just do a switch. So let's switch on the sort by value that you gave me. So if you told me to sort by the name, well, then we'll set sort stages, sort by the name ascending. If you told me that you want to sort by rating, well, then we'll sort by the rating average in descending order. And this works because the sort stage is after we did the project. So I can sort by the rating in descending order. I could sort by the the price and lowest price, and I might say, well, let's give me the lowest price. So I want price in ascending order, or if I want the highest price, then price in descending order. So these are basically the values that you would have in the dropdown. Or I want to say, let's sort by relevance, at which point I'll use the relevance if you've given me a query, because I can't really do relevance if you haven't given me some search keywords. And otherwise, I'll fall back to the name. So if we don't have a relevance score to go off of, I'll just sort it by the name. And as you'll notice, I have this word default in here. So if you don't specify how to sort it, then it's going to use this formula here. Does that make sense?
Yep.
So because I've specified that default, this will actually never end up being null. Got it? Because it would be a problem later if my sort stage was null. So, I mean, anytime you have a switch statement, you basically want to make sure that you include default. Also in there, remember to include breaks. You'll see I have a break for each of these cases. If you don't include a break, it's going to fall down to the next case, and you won't get what you want. So, for instance, if I left off this break, what's the sort stage going to be? If I say lowest price, will it be this?
It'd be the next one.
It'd be the next one, right? So it runs this line of code, sets it first to price ascending. There's no break here. It's going to go fall down here and set it to price descending. Got it? So make sure with the switches that you do include the breaks. So that's kind of how I dynamically build up the match stage of that and the sort stage of that. Now that first match stage that I created, this is just the first match stage. I still need to create that second match stage later, and we can see that as I start building up the pipeline. So the pipeline is an array, you can see here. So I put in that first match stage. You can see that here. I put in the lookup. The lookup doesn't change, so it's just hard-coded. Same way with the basically with project, with the exception of relevance. You see what I'm doing with relevance. I've got a ternary. So I say, if you've given me search terms, then spit out the relevance score. Otherwise, just use null. Because we can't do a text score if you don't do a text search. Got it? So relevance will either be a number or it will be null. And then here's my second match stage. So I say, if you've specified a minimum rating, then we'll put that in there. Otherwise, we'll just put an empty object. And so remember, an empty object effectively has no effect, right? It doesn't filter because there's no filter conditions. Cool?
Yeah.
So that one this one I could have done with a set of if statements as well, like I did previously, but because that's the only thing that can go in there, it's just shorter for me to write this as a ternary statement. So sometimes ternary statements are quicker. Sometimes, writing full-blown if statements are the easier way to go. And so you just kind of got to think about it, which way is going to be the easiest to read, depending on your particular scenario. Now that I've got that in, you can see the sort stage. I'm just injecting it. So $sort is sort stage. Skip is that same sort of formula that I told you about previously. Because we're starting at page 1, I say page -1 and then times the page size. Remember, these parentheses matter. If you don't have those parentheses, you'll get the wrong calculation. And then finally limit it to the page size. So that's my whole pipeline. Now, I've just built up this pipeline here. It's just an array. It hasn't actually been executed by Mongo. So I need to actually pass that pipeline onto the aggregate function. So here I'm going to say here I might say, let me comment this stuff out for now, because this is related to my streaming things. Here I would say, well, let's open up a connection to the database. So I'm going db.connect. And then I'm going to get a cursor. So I'm going to say connection.collection products. And let's say aggregate and pass in the pipeline, as well as the collation, which I had specified earlier up here. Okay. And the reason I'm specifying up here is that way later I could come back and change it and have it be, maybe something that the user enters. So maybe they want to set Spanish or something else. They could potentially set it in as a query parameter as well. So we say, let's do collection, let's do aggregate, and then finally, let's get the results using toArray, return those as JSON. Questions?
Nope.
Okay. So you kind of see how that Lego bricks together?
I was going to ask you something, Mr. Smith. So you know how every time we have to do the connection, the await database, why do we always have to do that? Why can't we just set in the db.js? Why do we always set in every method we have to do await db connect? Why do we always have to connect to it? Why can't it stay connected like MySQL?
Well, it is connecting. The thing is, we're not connecting until the first time you need it.
Okay, so
The thing is that the way that the connects thing is set up, it's kind of doing this underneath the surface. The way that connects is built, it kind of hides that connection. Okay.
yeah.
So there's not really a good way to hide. This is as best as you can do, basically, to hide it. Is call it connect, and connect's going to potentially take some time. Okay.
Yeah.
So it's by virtue of kind of how things work differently. That's kind of the best abstraction that you can get, unfortunately. Yeah. Okay, so that's how we build an aggregate pipeline like this. Is you basically use a bunch of if statements and switch statements like you're familiar with to build the individual objects and pieces that go into that. Okay, so there isn't really any sort of magic something in there. The one thing I would stress, and I that you don't want to do, is don't try to call aggregate more than once, right? Don't say, if this, then call aggregate this way. If this, call aggregate this way. What you want to do is put all your logic into building up that pipeline array. Cool? Because that will lead to a lot less code duplication and a lot easier to read code. So that's kind of how I build up those pipelines. There's a bunch of different ways, obviously, to do that, but yeah, the less code duplication, the better, generally. So let's talk about quickly how to analyze these queries. And get back into full screen mode. So oftentimes, once you've got these queries built up, you want to kind of look at some of the statistics of how they ran and what indexes they used, for instance. So in here, the way to do this, and this is going back to the shell. So I would say db.collection.explain, explain execution stats. So explain execution stats, you can call that on a collection or you can call that on a cursor. Those will give you different pieces of information that provide statistics about how your query ran. How many records did it have to look at? So to compare the performance of a query using different indexes, you can use the hint method in conjunction with explain. So hint will allow you to say, well, use this index and let's see what it would do if it was using this index instead. So these statistics that you get out of this can be really useful in measuring if and how a query used an index to see, does it really benefit from one of the indexes that you've added. So this is really important if you're trying to figure out, well, would a composite index make this faster, for instance? Or would adding this index make it actually work better? So to look at an example, let's say I've got this example data. So I've got these items. This is my inventory collection. So I've got IDs, I've got item. This is kind of almost a name for the item, what type, and what quantity, right? So I've got this example data here. And then I'm going to try and run the query. Quantity greater than or equal to 100, less than or equal to 200. So let's say we start this. First of all, we're going to start this with not having any indexes. Okay? So if we start this query with not having any indexes, let's see how it works. So I'm going to say find, and then I add to it .explain execution stats. So .explain execution stats says, I don't really care about the results. Just tell me how it ran and how many things it looked at along the way. So when I run that, it will give you quite a bit of data back. So I'm kind of abbreviating the results that this returns. So first of all, we've got the object that it returns starts with query planner. If you look into query planner, you'll find a property named winning plan. And winning plan tells you the stages that it ran through. So the winning plan is like an aggregation pipeline. So that it used. So the stage, it said call scan, short for collection scan. So if you see this call scan, you know that this query is having to look at the entire table, right? Look at the entire collection. That's a problem, right? So typically you don't want to see call scan there. If you're seeing call scan, that means it doesn't have an index that it was able to use. Okay. So you'll see that under winning plans. You'll also see that down if you look under execution stats, execution stages. It'll also say call scan down here as well. So both of those two things are a bad sign in general, because you want that to be based on an index, not looking at everything in the collection. Looking into the execution stats, you'll see some additional numbers there. So for instance, we see that it returned 3 results. We can see that the execution time in milliseconds was 0. Well, that's not really helpful, right? So because we don't have a lot of data, we only have 10 records here, the time was 0. Sheridan, did you have something?
No, sorry.
It's fine.
Control is my push to talk. So if I push
Yep.
control for anything, it just leaves.
Just checking. So we're getting 3 results back, but notice as we looked at this, so we didn't look at any indexes. So that's the 0 here. Total keys examined. We didn't use an index. But how many documents did we look at? Total docs examined. We looked at 10 documents. Okay. How many documents were in this inventory collection?
10, right?
10. So we had to look at every single document. Not a good sign, right? So I'd like the number of documents that we look at, I'd like that to be much smaller. I'd like it to be much closer to the number we actually returned, right? So what I want to do is I want to minimize this total number of documents examined, because that typically results in a faster query. You with me? Typically the most interesting number in there is how many documents it examined. That's the biggest thing that will tell you how fast or slow it's running. Because oftentimes you can't tell from the time because it may be so fast that it's 0. But it's also there's true that there's a lot of randomness in the execution time. So oftentimes you can't just look at, well, how long did it take it to run, and therefore infer that this is faster or slower. Usually you have to look at some of these other numbers like total docs examined to kind of expand and project and predict, is this going to be faster or the other, this way or that way, if I threw more documents at it. So if I instead, go add an index, let's create an index on the quantity. And why would I want to index the quantity? Well, if we look at the find, what column are we looking at? Well, we're looking at, is the quantity greater than or equal to 100 and less than or equal to 200, right? So we're finding based on the quantity column. So an index is going to be helpful, right? Index on the quantity is going to be helpful. So let's say we create an index on the quantity, and then let's try to run the query again with the explain on there. Okay, well now it's going to be an IX scan, short for index scan, instead of a call scan. You with me?
Yeah.
Yes, sir.
So an index scan is what you want to see there. You want to see IX scan. You don't want to see call scan. You don't want to scan the entire collection. So that's what you want to see to make sure that it's actually using the indexes that you provided. So if we look at that, we know it's using an index now. And we look at the number of records returned, right? Still 3. But look at what happened to total keys examined and total docs examined, right? So now because it's using the index, it looked at 3 index entries, which is pretty cheap, but it only looked at 3 docs examined. See that? So this is going to be much faster with that index because I have to look at fewer documents. Okay? So when you're adding indexes and you're trying to determine, do I need that index or do I not need that index, typically you want to use that explain and kind of look at, is it actually reducing the total number of docs examined? If it's not, then maybe one or two things. Maybe you don't have enough data to really test it, or maybe that index is really the wrong index. So that's how you can kind of look at the performance and see it. There's an additional performance optimization I want to mention. There's something called a covered query. If you get a covered query is where it can do the entire query just using the index. So here, in addition to those filter criteria, I've added a second argument, which is the projection. And this syntax is a little bit different because it's in the shell. The way you specify project in the shell is actually different than Node. But here it's the second argument to find. So I say ID 0, so don't include the ID and just return the quantity, which means that what this is going to be returning is just an array of quantities. Well, remember that the quantities are in that index, right? So with this here, now notice the total docs has gone down to 0. Does everybody see that?
Yeah.
Because it didn't need to actually go to the collection, because all the data was in the index. So it returned 3 documents. It looked at 3 index keys still, but this went down to 0. So, and it says projection covered. The stage is that, and inside of there's an IX scan. So if you see that there, that's what's happening. And sometimes you can do that in kind of some narrow cases to speed up your performance, your queries. Sometimes you can set it up so it only needs to look at the index and nothing else. That's a little bit beyond the scope of, what we'll talk about here, because sometimes to get this to work, you have to add additional things to the index, the indexes, which is a newer feature in Mongo. But just know that sometimes if you're playing around with it, if you see this coming up as total docs examined all of a sudden, that may be what's happening, is that you're getting a covered index. You're getting a covered query. Last topic in here is to talk about cursor streams and oboe. We are at 407. So take some time to work on your labs, and so you've got to start on thinking about these aggregation pipelines and text search and indexes. We'll talk about the streaming portion of this then tomorrow.
Okay, so we're not meeting again in person, right? For the rest of the semester? I have not heard anything as far as changes. So we are still planning to meet in person. So our plan is still going forward to meet on Tuesdays and Fridays. So we've got 5 days. We'll be in person tomorrow. Tomorrow I'll be on campus. What I will say, first of all, from Shannon, she's asked for sure. I mean, if you have any symptoms, if you feel ill, please stay home. If you have any reason of concern, please stay home. Please let us know, just in case we need to contact and do contact tracing. But please stay home if you are feeling sick. That being said, yes, these are the 5 days we are scheduled to be in. It's really up to you what you feel safe with. Does that make sense? So if you feel that it would be safer for you to stay home, then stay home. That's basically where we're at. So there hasn't been anything officially saying we're canceling classes. We're just monitoring for symptoms. So, if you feel safer at home, be safer at home. So I'll let you get on your projects and whatever else you need to do, and we'll finish up the second part of that, the last bit of that tomorrow.